Ever looked up at the sun and thought we had it all figured out? It's a giant ball of hot gas, right? Simple. Well, not quite. The truth is, the very heart of our solar system, the sun's core, is one of the biggest mysteries in modern science. We think we know what's happening down there, but we've never actually seen it. It's like trying to understand how a car engine works just by listening to it from a mile away. So what do we think is happening? The textbook answer is nuclear fusion. In the sun's core, the pressure is over 250 billion times that of Earth's atmosphere, and the temperature is a scorching 15 million degrees Celsius. In this extreme environment, hydrogen atoms are squeezed together so tightly that they fuse to form helium. This process, called the proton-proton chain reaction, releases an incredible amount of energy. This energy is what powers the sun and, ultimately, all life on Earth. It's the ultimate power source. This energy, born as powerful gamma rays, doesn't just shoot straight out. It begins an epic journey from the core to the surface. Imagine a pinball machine the size of a star. A single photon of light bounces randomly from atom to atom, getting absorbed and re-emitted over and over again. This journey, known as the random walk, can take an astonishingly long time, anywhere from 10,000 to over 170,000 years. So the sunlight that warmed your face today might have been created before human civilization even began. Think about that for a second. To see inside the sun, we can't use light. The sun is completely opaque. So, scientists got clever. They started looking for tiny, almost massless particles called neutrinos. Neutrinos are a byproduct of the nuclear fusion in the core, and they have a superpower. They barely interact with matter. They can fly straight through the entire sun in just 2 seconds and reach Earth in about 8 minutes, carrying direct information from the heart of the star. They are like cosmic messengers, delivering a real-time report from the core. Detecting these ghostly particles is incredibly difficult. Scientists have built massive detectors deep underground, like the Super Kamiokande in Japan, which is a giant tank filled with 50,000 tons of ultra-pure water. Every so often, a single neutrino from the sun will collide with a water molecule, creating a faint flash of light. By detecting these flashes, we can count the neutrinos and learn about the fusion reactions happening right now. It's a painstaking process, but it's our only direct window into the sun's engine room. And here's where things get really interesting. When we first started detecting solar neutrinos, we found a problem, a big one. Our detectors were only picking up about a third of the neutrinos that our models of the sun predicted. This was called the solar neutrino problem, and for decades it was a huge puzzle. Did we misunderstand the sun? Or was something wrong with our understanding of physics? It was a major scientific cliffhanger. The solution turned out to be even more mind-bending. Physicists discovered that neutrinos can change flavor. They come in 3 types: electron, muon, and tau. The neutrinos created in the sun are electron neutrinos, but on their way to Earth, they can spontaneously morph into the other 2 types, which our early detectors weren't designed to see. This discovery of neutrino oscillation was a massive breakthrough, not just for solar science, but for particle physics, and it even earned a Nobel Prize. The sun was a natural laboratory that helped us uncover a fundamental property of the universe. So, problem solved, right? We figured out the neutrinos, so we must know everything about the core now. Not even close. Neutrinos have confirmed that fusion is happening, but they've also opened up a whole new can of worms. Our current models of the sun are good, but they're based on averages. They assume the core is a smooth, stable, and perfectly predictable furnace. But what if it's not? Think about a pot of boiling water. It's not perfectly smooth, is it? There are currents, bubbles, and eddies. It's a chaotic, dynamic system. Could the sun's core be similar? Our neutrino detectors are getting more sensitive, and they're starting to hint that the fusion rate might not be perfectly constant. There could be tiny fluctuations, small surges, and dips in the energy production that our current models don't account for. These aren't just random guesses. Some theories propose that there could be waves or oscillations deep within the core. Think of them as G-modes or gravity waves, sloshing around inside the star. These waves could slightly stir the material in the core, causing small, temporary hotspots where the fusion rate spikes, or cool spots where it dips. We're talking about very subtle changes, but detecting them would revolutionize our understanding. It would be like finally being able to hear the individual cylinders firing in that car engine, instead of just a distant hum. Another mystery is the precise composition of the core. We assume it's mostly hydrogen and helium, but there are also trace amounts of heavier elements, which we call metals in astronomy. These metals play a crucial role because they affect how opaque the sun is, which in turn affects how energy gets out. But our measurements of these metals from the sun's surface don't quite line up with what our models of the interior, based on helioseismology, the study of solar quakes, tell us. This is called the solar abundance problem, and it suggests our picture of the sun's structure is still missing a key ingredient. So, how do we solve these new mysteries? We need more data, and better data. The next generation of neutrino observatories, like the DUNE experiment in the US and Juno in China, will be even larger and more sensitive. They'll be able to measure the energy of solar neutrinos with unprecedented precision. By doing this, they could potentially detect those tiny fluctuations in the fusion rate. If we see a pattern in how the neutrino count changes over days, months, or years, it could be the smoking gun for waves or other dynamic processes in the core. It's a quest to understand the most fundamental processes that govern not just our sun, but stars throughout the universe. Every star you see in the night sky is powered by a similar engine, but each has its own quirks. By peeling back the layers of our own star, we learn more about the cosmos as a whole. The sun's core is a place of unimaginable extremes, a place we will never visit. But through human ingenuity, using ghostly particles and the echoes of solar quakes, we are slowly but surely beginning to map out this hidden realm. The next decade of solar physics promises to be incredibly exciting. We stand on the verge of potentially confirming or refuting decades-old theories about the inner workings of stars. What we find might force us to rewrite the textbooks all over again. The sun, our constant companion in the sky, still has so many secrets to tell. And that's what makes science so thrilling. The biggest discoveries often lie hidden in the places we can't see. Thanks for joining me on this journey to the center of the sun. If you found this as fascinating as I do, make sure to like, subscribe, and hit that notification bell so you don't miss our next dive into the mysteries of the cosmos. See you next time.